In this video, we talk about coordinate changes and changes of basis. A quick reminder about spanning sets. Given a vector space V, we find a collection of vectors V1, V2, and so on, such that every element of V is a linear combination of those vectors. So in other words, we find a collection of vectors which span V. And this collection is called a spanning set. We call vectors linearly independent in vector space V if none of those vectors is a linear combination of the others. Or equivalently, vectors V1 and so on, V2 and so on are linearly independent if the sum CI/VI is equal to 0, if the only linear combination which is equal to 0 is a trivial linear combination. Another recollection of definitions of the basis. So a subset V1, V2, and so on of a vector space V is a basis of V if it is linearly independent and spans V. Yet another way to write the definition is that there's a subset V1, V2, and so on of a vector space V. It's a basis if there is one spanning and only one linear independence way to write any element V inside big V as a linear combination of the little vi's. Here's an example. The canonical basis in 3 dimensions is the first example. Second example is the vectors 1x, x squared as a basis of polynomials of degree 2, at most 2. We'll call P2.
Sorry.
Yeah, I was checking.
You can use your mask.
What?
You can use your phone.
Yeah, I have a mask, but I'm speaking.
Oh, okay.
Yeah. Once again, example 1x, x squared is the basis of polynomials of degree at most 2. Definition of linear transformation, right? So the transformation is linear if it behaves in the following way on two vectors, right? So V1 and V and V prime are vectors in V, and this is how this linear transformation behaves. Now, one more reminder about one-to-one and onto maps. So if we have a function f from x to y, it is said to be onto if every element of y is image of some element, or at least one element from x. It's one-to-one if every element of y is an image of at most one element of x. So it's either one or none. Now for linear transformation T from Rm to Rn, we know that there is a one-to-one correspond map if and only if the columns of the associated matrix are linearly independent, and it's onto if and only if the columns of the associated matrix span the codomain. So among all functions, the one who was distinguished, namely it's the identity function that does nothing. So it takes x and then returns back x. So it's id_x. It is a linear transformation, as we discussed. When x is equal to Rn, the matrix id_x is the identity matrix, and n by n identity matrix. Now, function f from x to y is invertible if there is some function g from y to x, with these two compositions being identities in x and y respectively. So when x and y are vector spaces and f and g are linear, and the matrices of f and g are inverses. So to each other, so they multiply to be the identity matrix in each order, depending. Yeah. So matrix for g multiplied by matrix of f is equal to identity in x and vice versa. So as with matrices, if inverse exists, then it's unique, and we write it as f inverse. Isomorphism, so invertible linear transformations are called isomorphisms. If there's an isomorphism from V to W, we say that V and W are isomorphic vector spaces. So isomorphic vector spaces look the same to linear algebra. So for example, we looked at the example, the previous two examples with the three-dimensional Euclidean space and the space of polynomial functions with degree up to 2. They are isomorphic as vector spaces, albeit they look completely differently otherwise. Yes. So if you ask one question to one of those spaces and you answer it in any way, it will give you, it will provide you the answer for the same question for the other linears, for that vector space, which is isomorphic to the first one. So we can use isomorphism F to translate back and forth. So if we have a linear transformation T from V to W, then the following four statements are equivalent. T is one-to-one and onto. T is invertible. So its inverse is linear function. T takes some basis of V to a basis of W. And then also T takes any basis of V to sum to a basis of W. Now, bases, coordinates, and parameterizations. So given a vector space V and the basis little vi of V, and the vector space W and any elements Wi of W, we can find there's a unique linear transformation T from V to W, which takes Vi to Wi and the corresponding linear combinations to the corresponding linear combinations. So for any elements Wi of W, we have a linear transformation from Rn to W, which takes the canonical basis of Rn to elements Wi, and then therefore, because of that, it would take the tuple A1, A2, and so on, An of the coefficients of the linear combination of those vectors into this linear combination. So if Wi's they form a basis, so notice we haven't discussed the dimension of W yet. So if they do, right, in this case, W should be a n-dimensional vector space, then this linear map is an isomorphism. And we call this isomorphism a parameterization of W. In other words, it's the tuple of numbers that parameterize the sort of in a given basis, right? Which parameterize the linear combination of those vectors. We can construct its inverse map, and this inverse map is called a choice of coordinates on W. In other words, it tells you. So since in the canonical basis of Rn, there's a natural notion of the order of coordinates, right? So E1 goes first and so on. So that's how, by using the inverse of this map, we can assign the coordinates to W. Well, example, take elements 1, x squared, and so on, x to the n, which form a basis in this space of vector space of polynomials of degree up to n. The Pn is isomorphic to Rn plus 1, right? So let's see how, so obviously you can just assign this E1 to 1, E2 to x, and so on, En plus 1 to xn. This way you have a parameterization. A basis B, V1 through Vn of a vector space, capital V, thus determines a choice of coordinates via this isomorphism. So for V, little v from capital V, you can write V sub B or the image of V under this map. right? So it's just it will be, if you wish, it's the order number of that vector in the basis. So by uniquely expanding it like this, we have this essentially it's this coefficient here, which are the appear in the linear combination. So take basis. Before we took a standard basis in P2. Now let's take a slightly non-standard basis. So it's 1, x plus 1, x squared plus 2x plus 1. And let's find the image of this polynomial here, 4x squared plus 2x plus 2, under the choice of the coordinates. So in other words, we need to find these coefficients, right, C1, C2, C3, such that the linear combination of basis vectors from D will give us the sought polynomial, the 4x squared plus 3x plus 2. So we can convert it into a system of linear equations, right? You just open up the parentheses and you combine terms and you factor the terms with the same power of x. And this yields us the following three equations. And you can solve them to get C1 equals to 3, C2 equals to -5, and C3 is equal to 4. Yeah. You can check that this is a solution. Or you can solve it by yourself. So this is, the matrix is already in echelon form. It's not in a reduced echelon form yet. I hope you can find the solution easily. Now let's talk about change of basis. The basis allows us to treat an arbitrary finite dimensional vector space as if it was just Rn. So that's the kind of the power of linear algebra, that if you're only interested in the in linear properties of those functions or those objects, it essentially says, since all vector spaces of the same dimensions are isomorphic, that the change of basis will allow you to, so these two maps that we talked about, the parameterization and the choice of basis, they allow you to treat any vector space as if it was the n-dimensional Euclidean space. And depending on the problem, one choice of basis may appear to be more convenient than another. So, and of course, sometimes we should be able to switch. So we want to be able to change this, to replace the map by a different one at will. So given two bases, B and C of V, and given an expression V in basis B in one of them, we would like to find an expression V in C in the other. So we're looking for a transformation of this form. It's called P from B to C, and then you see why I put the arrow in the opposite direction, such that, well, so you should treat this as a symbol, as one symbol. So that it's a change of basis from B into C. And so that if you apply the symbol to V sub B, you get a V sub C. So as we'll see, it will be a linear transformation. You can write it as this triangular diagram, right? So V is the vector space here, and then there are two bases, two choices of coordinates. So V, there's this map, there's a basis B, which sends it to Rn, and then there's a basis C that sends it to Rn. And this transformation, P, B goes to C, is directed from this Rn to that Rn. So it's a linear transformation between two n-dimensional Euclidean spaces. Okay, so that's what we're looking for. So we should be able to write this as a matrix, because that's the map from a linear map from Rn to Rn, and that's what basically matrices are designed for. Now, to figure out which matrix, we should see where this map sends the vectors, the canonical vectors of the canonical basis EI. Say basis B is given in terms of n vectors B1 through Bn, basis C is given in terms of C1 through Cn. Here's the diagram that we are studying. So it takes vector Bi from vector space V and sends them to so since this leg here, so this arrow, so this arrow corresponds to the basis B of V, right? It by design, by construction, sends the vector Bi into vector EI. And then here, this is, and then the other arrow, it sends the vector Bi into its image in basis C. So we want to try to figure out how this reparameterization, the change of basis operation, what it does with EI. So we know what it does, right? So from this diagram, it takes EI and then sends it to image of vector Bi under the second map. Okay. So, and then since we know what the matrix, that matrix does, right? It takes, so in other words, the ith column, which is what represents what EI represents itself in the matrix. The ith column this is the ith column of the matrix of this, the ith column of the matrix of this linear transformation. P B goes to C is the image of vector Bi under the second basis. Is BIC. Okay, so let's look at an example. It may look a little bit abstract if you see it for the first time. So consider two bases, which we have already looked at before. One x squared, which is in a sense the analog of the canonical basis, and P2, and then this basis C, 1x plus 1x squared plus 1 squared plus 2x plus 1 as two bases in the space of P2. So what's the matrix for the change of basis here? Well, so these guys, right? So the columns of this linear transformation on the change of basis will be the images of these three vectors under the basis B, right? So it's 1b, x plus 1b, x squared plus 2x plus 1 sub b. And if you write it as a matrix, right? So if you write it as the, now, so it's not, in other words, now you need to expand them in terms of these elements, right? So, so we have 1 here, 1, 1 here, because it's x here and 1 there, and then here we have 1 to 1, according to the formula. So in this case, it's an upper diagonal matrix. Okay, and now let's go backwards, right? So let's just show again. So right, so this is the matrix change of basis from C. It's from C to B, right? So it was C to B, and this is upper triangular matrix like this. And now try it yourself. So before we go, pause the video and do the calculation, which changes B into C. In other words, we need to re-expand. We need to expand each of those numbers in terms of these polynomials, and then find the coefficients of the corresponding expansion. Okay, so resume the video once you're done. Okay, so now what these guys are. So that's what they are, right? So here, so 1 obviously goes to 1, and then x, to get x in terms of these vectors, you can take x plus 1 and subtract 1. So that's why there's a minus 1. That's why it's minus 1, 1. And then to get x squared, you need to remove the 2x plus 1 from here, right? And then to do it, you can multiply second vector by minus 2, and then first vector, and then add that, and then add the first vector. So this way you'll get rid of that. So this is how this matrix looks like. So the matrix of change of basis from C to B is 1, 1, 1, 0, 1, 2, 0, 0, 1. Matrix of change of basis from B to C is 1, minus 1, 1, 0, 1, minus 2, 0, 0, 1. Okay, multiply. As by now you should expect what you're going to get. And you should be able to get the unity matrix, right? So well, as you can clearly see from here. So change of basis happens by the inverse, right? Because you can take this diagram and then you can just swap those arrows, swap the left and right arrows, and then here this map from this Rn to that Rn is P B to C, and map from this Rn to this Rn is map P from C to B, right? And therefore they have to be just by combining these two diagrams, they have to be an identity, right? So if you change basis from C to B, and then you change basis from B to C, right? You ought to have the same, right? The identity operation. So you can sort of combine these two Rns together. So you take element from here, change it there, and then change it back. So it has to be an identity operation. So yeah, if you want to find the change of basis matrix, if you know the other one, you just do the inverse. Now consider the special case when the vector space is Rn. So now we have a triangle where in each vertex in which we have Rn, and then we have in sense every leg is some matrix. So you can, in other words, you can treat those choice of coordinate maps as changes of basis. From the standard basis to B or C respectively. So let's write STD for standard or for the canonical basis, and then we can write it like, so there's a change of basis P from standard to B, and then changes of P from standard to C. This is what they are, right? So therefore, based on what we know, it's easy to write a formula for the change of basis from, say, B to standard, right? Since in standard basis, the image of V is just V, right? It's simply just how you expand your vector. What are the coefficients of the expansion in the standard basis? And then the matrix of this change of basis transformation is simply formed by the column vectors, which are nothing but B1 through Bn. So therefore, this choice of basis operation is identical to the change of basis operation from standard to B, and therefore it will be inverse of this matrix, right? Because the matrix, here we have the matrix of B into standard is formed by columns of B1 to Bn. Therefore, to find the B matrix, we need to take the inverse of that, right? So it's this guy, right, is the change of basis from standard into B. And according to our rule, You just need to take this matrix and invert it. And similarly, the change of basis operation, or the basis operate, the choice of coordinates for basis C, aka the linear transformation, aka the change of basis from standard into basis C, is equal to the inverse of this operation, or inverse of this matrix. And finally, we can compose, right? So therefore, we can use this, in other words, we can use the standard basis as an intermediary, as an intermediate step in order to find the change of basis matrix between bases B and C. So therefore, if you follow what we just said, the change of basis transformation from B into C is equal to the product in this order of the change of basis from standard into C times that of change of basis from B into standard. And the inverse transformation, the other change of variables, P, C to B, will be the product of these guys in the different order. So in the first case, you're going to get the inverse of the matrix formed by columns of C's times matrix of B's. And in the second case, you get BI, this matrix B inversed times matrix C, matrix front of column C. So if you wish, there's some sort of mnemonic rule which will help you to memorize that. So if you have P, B to C, just write two matrices, and then in the middle there's a standard basis, which you sort of dot with each other. Let's look at an example. Let's determine the change of basis matrix P from B to C from basis. So we take two-dimensional Euclidean space, and then there's a basis 1, 2, 3, 4, and the basis 3, 4, 5, 7. So, well, we just saw the formula, right? So that's just compose them in this way. That's B guy, so we go B to C, so for its first guy standard to C, and then standard to B, B to standard. So we take the inverse of the matrix of these guys, and then times the matrix formed by column from these guys, right? So it's 3, 4, 5, 7 inverse multiplied by 1, 2, 3, 4. So you can easily invert this 2x2 matrix and do the multiplication, and that's what we get. You get negative 3, 1, 2, 0. Now, if B is a basis in V and C is a basis in W, a linear transformation can be written from V to W, is written in coordinates by the matrix C with two indices, C and B, right, which would complete the square now. So say you have T goes from V to W, right, and then we can take, so here, the dimensions of V and W, they don't have to be the same anymore. So but we know that V is a linear space, is a vector space, so we can pick a basis, right? So we can map it to the R to dimension dim V, right? So if V is dimension is N, it will be Rn. If W is dimension is M, Michael, it will be Rm. So this matrix that we're talking about would complete this commutative square, what we say, right? So you can either go horizontally and then vertically, or can go vertically and then horizontally. You must arrive at the same element here. So for a new choice of basis, B prime of B and C prime of W, we have this situation here, right? So if we had an old matrix CTB, then we need to multiply by it from the left with the change of basis from C to C prime, and on the right from the change of basis from B to B prime to B. See, like so that the neighboring indices are the same, and you can think of them as they're contracted, right? So if you have some intuition from say physics literature, then that this index contraction always happens there. Okay. Yes. And in a special case when V and W are identical or isomorphic, and B is equal to C, then we can just write T with index B, right, which corresponds to this matrix. So, and for this new choice of coordinates, if you have take a basis B prime in vector space V, then we take formula from the previous slide, and then we know that P goes to B prime is the P prime goes to B inverse. So therefore, this is how we can do it. So in other words, if you take the, right, so meaning of this formula is the following. So if you have a linear transformation from vector space V to itself, then under the change of basis, the matrix of linear transformation TB is transformed like this. So that you take the matrix of change of basis and then you multiply inverse of that by your matrix and then times this times the matrix of the change of basis. Okay. And then finally, when V is literally Rn, right? So then, well, we have the same diagram. And then recall that those images here are, so VB is equal to this change, the inverse matrix B1, which formed by columns B1 and Bn inverse acting on V. So we can write the change of basis, change of the, excuse me, the new form of the matrix of linear transformations under the change of basis like that, right? So, so in other words, so say we should think of it like this. Say we have a linear transformation from Rn to N. Now, how can we write its matrix? Well, it's written like that.